Hey everybody. Today we're talking about marginal probability distributions of continuous random variables. We're in a situation where we have two random variables, let's call them x and y, and they have a bivariate distribution. In other words, they might be related to one another, we don't know yet. We describe such a joint distribution using a joint probability density function, or joint PDF, typically written f of x comma y. And then we compute probabilities using double integration. If we have any subset of, call it d, of r squared, then the probability that x and y land in that region is just the integral of that joint PDF over that region. Now we can also consider the two random variables separately, sort of one at a time, considering probabilities for x or y alone. And those are called marginal distributions. Those marginal distributions have PDFs, of course, and we need to denote those with f sub x of x and f sub y of y. So the subscript is reminding you that it is a marginal distribution with respect to that variable, and then the inside of the function is just, of course, the value of the random variable that you're interested in. We compute marginal PDFs by integrating out the other variable. So, for instance, to find the marginal PDF of x, f sub x of x, we integrate that joint PDF f of x comma y from y equals negative infinity to y equals positive infinity. I think all this gets a little more clear when we have an example, so let's jump right in with one. Let's have two random variables, x and y. They're both of the continuous type, and their joint PDF is 1/16 x plus 3y. The support is 0, 2 cross 0, 2, so basically x and y both range from 0 to 2. Find both marginal PDFs and then use them to compute the probability that x is less than 1 and that y is less than 1. So I recommend pausing the video here using the definitions from the previous slide to try this on your own before seeing my solution. Starting with f sub x of x, we're taking the joint PDF and integrating it with respect to y. Now, technically, we're integrating from negative infinity to infinity, but f of x comma y is only non-zero when x is between 0 and 2. So that means we can just integrate from 0 to 2. We're integrating with respect to y, which means treating x like it's just a constant. And when we do out all of the arithmetic and plug in y equals 0 and y equals 2, we get that the joint PDF of x, f sub x of x, is x plus 3 over 8. Similarly, we can do f sub y of y. This time we're integrating with respect to x and plugging in x equals 0 and x equals 2. This time treating y like a constant. In the end, we get f sub y of y is 3y plus 1 over 8. Now, every marginal PDF is a normal probability density function in its own right, and they satisfy the properties of probability density functions. They're always positive, and they integrate to 1. So, for instance, f sub x of x is the probability density function for x on the interval 0, 2. And if we integrate that from 0 to 2, we get 1. And I recommend verifying that for at least one of these on your own. Now that we have those marginal PDFs, we can compute probabilities like, x less than 1 and the probability that y is less than 1, just in the usual way. Those are single variable questions. For instance, the probability that x is less than 1 is the integral from 0 to 1, from x equals 0 to x equals 1, f sub x of x dx, that is, we're integrating x plus 3 over 8 from 0 to 1. When we do that, we get 7/16. Similarly, the probability that y is less than 1 is the integral from 0 to 1 of the marginal probability density function of y, 3y plus 1 over 8. When we do out that integral from 0 to 1, we get 5/16. Expected values of marginal distributions are calculated just as they are in the single variable case, and that makes sense because once you're talking about a marginal probability distribution, you've basically gotten yourself to a single variable situation. So for instance, the expected value of x is the integral from negative infinity to infinity x f sub x of x dx. And that's just your ordinary definition for expected value for a single random variable. That same observation holds when we're talking about variance. We compute marginal variance by just doing your regular single variable variance. Typically, we do that using the formula that the variance of a random variable is the expected value of the square of the random variable minus the expected value of the random variable squared. So for instance, the expected value of x squared would just mean integrating over the entire support of the random variable, or from negative infinity to infinity, x squared f sub x of x dx. Let's carry on with that same example that we were looking at earlier and use it to compute the expected value and variance of y. So again, I recommend pausing the video, trying to do this on your own before seeing my solutions. We already have the marginal PDF, f sub y of y. It's 3y plus 1 over 8, and we know the support is from y equals 0 to 2. So to find the expected value, we are going to integrate y times f sub y of y. You can see the math here. In the end, we get 1.25. So on average, if we run this probability experiment many, many times, getting random values for x and y with this joint distribution, on average, the results will be 1.25. The calculation for the expected value of y squared is almost identical. This time we're integrating y squared f sub y of y dy, again from 0 to 2. When we do out that math, we get 11/6. Using that, we can now get the variance of y. We're doing the expected value of y squared minus the expected value of y, quantity squared. When we do that out, we get 0.27. By taking the square root of that, we get the standard deviation of y, just a little more than 1/2. So if we do this probability experiment many, many, many times and just look at the result y, on average we get 1.25, and on average individual draws will differ from that mean by about 0.52 on average, roughly speaking.